On July 23, 2012, the Sun fired a direct shot at Earth. A coronal mass ejection as powerful as the worst solar storm in recorded history launched straight through the point where our planet had been orbiting just 1 week earlier. 1 week. That's all that separated us from trillions of dollars in damage and a power grid that might still be recovering today. But here's what nobody tells you. That event, the one that almost ended modern civilization as we know it, wouldn't even rank in the top 10 of what the Sun has actually done before. Tonight we're going through the full story of what our star is truly capable of. So settle in and get cozy. This one goes places you won't expect. Part 1. The Sleeping Giant. If I told you that right now, at this exact moment, there is an object 43 million miles away that is actively trying to kill everything you love, you would probably think I was exaggerating. But I'm not. What I'm about to walk you through is the story of how scientists kept discovering that they were catastrophically wrong about the dangers our Sun actually poses, and how each time they thought they'd found the ceiling of solar destruction, the evidence forced them to revise their estimates upward. Every single time. And the most unsettling part, we are currently living in a moment when the Sun is becoming more dangerous, not less. Let me start by painting you a picture of what's actually happening on the surface of the Sun right now. Close your eyes for a second and imagine something unfathomably hot and violent. Now imagine that's the outside. The photosphere, the visible surface, is churning at 5,500 degrees Celsius. That's hot enough that if you could somehow teleport there, don't worry, you would be vaporized before you felt pain. You would experience something that looks less like a sphere and more like a cosmic ocean mid-hurricane. Convection cells, each one roughly the size of the state of Texas, bubble upward from the interior, cool slightly, and sink back down. The entire surface is in constant motion, a slow-motion boil that has been happening for 4.6 billion years and will continue for another 5 billion more. But the really important thing, the thing that makes the Sun into a threat rather than just a hot ball of light, is what's happening with the magnetic field. The Sun generates an absolutely colossal magnetic field through the movement of charged plasma far inside its interior. This field arches out from the poles and loops back through the equator in structures that can span hundreds of thousands of kilometers. To give you a sense of scale, that's larger than the distance from the Earth to the Moon. These loops, these brilliant structures you can see during a solar eclipse, are not decorative. They are the stress lines in a machine that stores incomprehensible amounts of energy. Here is where it gets interesting, and here is where we start building toward why the Sun has been scarier than we ever wanted to admit. The Sun does not rotate like a solid object. It is a ball of plasma, and different parts of it rotate at different speeds. At the equator, the Sun completes one full rotation every 25 days. At the poles, it takes 36 days. That's 11 days of difference. Imagine taking a rubber band, stretching it, and then twisting the two ends at different speeds. What happens? The rubber band winds tighter and tighter and tighter. The tension builds. The stored energy accumulates. Eventually, if the twist goes on long enough, that rubber band is going to snap. That is what the Sun's magnetic field is doing all the time, on a scale that would make any rubber band look quaint. The result of this process follows a rhythm that solar scientists have been tracking for centuries. The Schwabe cycle, discovered in the 1800s by a German amateur astronomer named Samuel Schwabe, runs for approximately 11 years. During this cycle, the number of sunspots rises and falls. Sunspots are dark spots on the solar surface caused by intense localized magnetic fields, and they are visible even to the naked eye when the Sun is low on the horizon. Schwabe noticed that the number of sunspots follows a periodic pattern. 11 years of quiet, then 11 years of chaos, then quiet again. It is perhaps one of the most fundamental rhythms in our solar system, and nobody fully understands what drives the precise timing, but it gets more complex. There is another cycle layered on top of the Schwabe cycle called the Hale cycle, named after George Ellery Hale, who discovered in 1908 that the Sun's overall magnetic polarity actually flips every 22 years. So while the 11-year cycle tracks the rise and fall of sunspot activity, the 22-year cycle tracks the orientation of the magnetic field itself. During the first half of a Hale cycle, the magnetic field points one direction. During the second half, it flips and points the opposite way. This flip coincides with the solar maximum, the moment when the Sun is at its most active and most dangerous. We are currently living in the ascending phase of solar cycle 25, which began in December of 2019. And here is where the story becomes immediately relevant to you, today, in 2026. Solar scientists predicted that solar cycle 25 would reach its maximum with a smoothed sunspot number of around 115. This is what they expected. This is what their models said. This is what they published. But the Sun, as it turns out, does not follow human predictions very carefully. The actual peak, measured in October of 2024, reached a sunspot number of 161. That is 46 points above the prediction. That is a 40% overshoot, and the activity has not declined the way the model suggested it should. Through the entirety of 2025 and into 2026, the Sun has remained unusually active. We are not past the danger window, we are in it. The cork on the bottle has not popped yet, and the pressure is still building. This matters because solar maximum is when the probability of extreme events spikes dramatically. It is when the twisted rubber bands are most taut, when the energy is most compressed into the magnetic field structures. It is when a single trigger could release everything at once. Scientists describe it as a shift from a simple dipole configuration during solar minimum toward a more complex multipolar field structure during maximum. What that fancy language is actually saying is that the magnetic field becomes increasingly tangled, increasingly unstable, increasingly ready to snap. And when I say snap, I do not mean a small release. I mean an explosion that makes nuclear weapons look like birthday candles. But before I describe what happens when all that energy lets loose, I want you to understand something about the timeline you're living in. The Sun has been in a phase of relatively calm behavior for most of your life. The storms of the 1980s and 90s were significant, but nothing catastrophic. Solar cycle 24 was weak by historical standards, peaked in 2013 or 2014, and people in the field actually worried that the Sun might be entering a prolonged quiet phase called a grand minimum, where activity would plummet for decades. That would have been a relief. Instead, the Sun had other plans. Solar cycle 25 came in hotter than anyone expected, and we are still very much in the active phase of that cycle. The danger window is open, and the current moment has more in common with the fearful solar activity of the early 1900s than it does with the relative calm of the early 2000s. So what happens when all that magnetic energy finally does release? What does it look like when the twisted field lines suddenly unwind, when the rubber band finally snaps? Part 2. When the Sun snaps. Let me explain the way we classify the destructive power of a solar explosion. Scientists use what is called the X-class scale. It runs from A through B through C through M through X, and each step up is a 10-fold increase in energy released. An A-class flare is tiny, barely measurable. A B-class flare is 10 times stronger. A C-class flare is 10 times stronger than that. Then we get to M-class, where things become genuinely destructive. An M-class flare is 100 times stronger than a C-class flare. And then we get to X-class, where the scale officially becomes open-ended. An X-class flare is 1,000 times stronger than a C-class. An X10 is 10 times stronger than an X1. An X50 is 50 times stronger than an X1. Let me put that in some kind of human terms. An average C-class flare releases energy equivalent to approximately 1 billion hydrogen bombs. 1 billion! If that sounds incomprehensibly large, that is because it is. The largest nuclear weapon ever tested, the Soviet Union's Tsar bomber in 1961, had a yield of about 50 megatons. 1 billion hydrogen bombs would be 50 billion megatons. An X-class flare is 1,000 times more powerful than that. You're now at 50 trillion megatons, and that is just an X1. An X10 is 10 times stronger. An X100 would be 100 times stronger than that. The mechanism that creates this explosion is called magnetic reconnection, and it is actually not that complicated once you understand the basic idea. Remember those twisted magnetic field lines I described, the ones arched across the solar surface? When they get twisted tightly enough, they create regions where the field is incredibly stressed. There is so much potential energy packed into such a small volume that eventually the field essentially snaps. The field lines, which were arched in one direction, suddenly flip to a different configuration. When they do this, they release all the energy that had been stored in that stress. The charged particles in the plasma are accelerated to nearly the speed of light, cascading down through the solar atmosphere. The temperature rises explosively. The light across every part of the electromagnetic spectrum intensifies. From radio waves to X-rays to gamma rays, the sun suddenly screams. That is what a solar flare is, and CMEs, coronal mass ejections, are what sometimes accompany the most powerful flares. A CME is when the magnetic reconnection is so violent that it ejects billions of tons of plasma into space at speeds sometimes exceeding 600 miles per second. The solar wind, the constant stream of charged particles flowing outward from the sun, suddenly becomes a roaring plasma tsunami. It rushes past Mercury, it approaches Venus, and if Earth is in the way, it delivers a tremendous impact to our planet's magnetic field. For most of the modern age, the largest flare ever recorded was thought to be an event called the Halloween storms of 2003. In October of that year, the sun unleashed a series of eruptions that were so powerful they completely overwhelmed the satellites we use to measure solar flares. The detectors on the GOES satellites, which are the primary instruments we use to monitor X-ray flares, literally saturated. The instruments could not record anything higher because they were not designed to measure events that powerful. When astronomers first reported the data, they said the largest flare was approximately an X28. But later, scientists from the University of Otago in New Zealand used an entirely different measurement technique. They looked at radio wave ionospheric modelling, at the way the flare disrupted Earth's upper atmosphere, and they back-calculated the actual energy released. Their conclusion was that the Halloween flare was closer to an X45, possibly even higher. To give you a sense of what that means, an X45 is more than twice as powerful as the previous record holder, which was an X17 from 1989. It is 10 times more powerful than an X4.8, which was the previous record before that. We were breaking records by orders of magnitude. The Halloween storms destroyed the ADEOS-2 satellite, a billion-dollar Japanese satellite, and it simply ceased to exist. The radio blackouts were global. You could not use long-range radio communications anywhere on Earth. The aurora was visible at unusually low latitudes. It was by any measure the worst solar event of the satellite era, and every scientist in the field pointed to the Halloween storms and said, "Okay, that is the ceiling. That is the worst the sun can do. We have satellite records going back to the 1960s. We have instruments designed to capture these events." The Halloween storms were approximately X45, so the limit is somewhere in the X40 to X50 range. We should design our systems to handle events of that magnitude, and we should probably be fine. That would have been comforting. It would have meant that the Carrington Event, this thing that happened in 1859 that I keep mentioning, was an anomaly, an outlier, something that might happen once every few hundred years, unlikely to affect us again in the near future. Except here is what every scientist, every institution, every government planning document missed. The Halloween storms happened in 2003. They were supposed to be the worst, the baseline, the reference point, the top of the scale. But in 1859, something happened that was so much more powerful than the Halloween storms that the Halloween storms would have looked like a candle flame next to a wildfire. Part 3. The Day the Sky Caught Fire. September 1st, 1859. The Royal Observatory in Greenwich, London. An astronomer named Richard Carrington, one of the leading solar observers of his era, was doing what he did almost every day. He was at his telescope, pointing it at the sun and sketching the sunspots he could see on the solar disk. Carrington used dark filters to make the observation safe and to get a good view of the surface details. He was sitting at his drawing desk, pencil in hand, documenting what he was seeing, when something unprecedented happened. At approximately 11:18 a.m., two brilliant patches of intensely white light broke out on the sun's disk. Carrington described them as being fully equal to the brightness of direct sunlight, even through the dark filters. They were not subtle. They were not borderline observable. They were blazingly obvious. Carrington watched them, sketched them, and noted the time with precision. After about 5 minutes, the light faded. The white patches disappeared, and Carrington had no way of knowing that he had just witnessed something that would not be equalled for more than 150 years. But here is the remarkable part. Because at almost the exact same moment, in a different location, another astronomer was observing the sun independently. His name was Richard Hodgson, and he was at his observatory in London as well, but far enough away that there was no possibility of communication or collaboration. Hodgson saw the same white light. He recorded the same time. He published his observations alongside Carrington's. Two independent observers in two different locations documenting the identical phenomenon. There was no doubt. Something huge had just happened on the sun. The measurement of this event became even more precise when we look at what happened at Kew Observatory, where a physicist named Balfour Stewart was monitoring magnetometers, instruments that measure changes in Earth's magnetic field. At 11:20 a.m. on September 1st, just 2 minutes after Carrington and Hodgson saw the white light, the magnetometer traces suddenly jumped. The magnetic field on Earth lurched. It was like someone grabbed the needle and yanked it sideways. Stewart called this sudden disruption a magnetic crochet, from the French word meaning to hook or jag. It was the signature of something violent having just arrived at Earth's magnetic field. The question was, how fast did the Carrington flare get to Earth? A CME is fast, but it is not instantaneous. Normally, a CME takes between 3 and 5 days to travel from the Sun to the Earth. But this time, something was different. The magnetometer disruption at Kew occurred approximately 17.6 hours after the initial flare. 17.6 hours. Not 3 days, not even 1 day. 17.6 hours. To put that in perspective, if you left New York at sunrise and drove a car across the United States at a constant speed, it would take you about 40 hours to reach Los Angeles. The CME from the Carrington Event arrived at Earth faster than you could drive across the country. The implied speed of that CME was roughly 2,000 miles per second, which translates to 3,200 kilometers per second. That is about 6% the speed of light. In some analyses, scientists have proposed that a prior CME from August 29th may have cleared a path of lower density plasma through the solar wind, allowing the Carrington CME to accelerate to these extraordinary speeds. But that is still speculative. What we know for certain is that the fastest CME ever recorded arrived at Earth in under 18 hours. And here is something worth sitting with for a moment. For 153 years after the Carrington Event, scientists used it as the baseline. It became the gold standard of solar violence, the absolute worst-case scenario. Every time a new flare occurred and scientists wanted to assess how bad it was, they looked at it and said, well, is it bigger than Carrington? If it was not bigger than Carrington, then it was manageable. It was survivable. It was something humanity could absorb. The Carrington Event was the ceiling. It was the limit. It was the benchmark. The reason scientists felt comfortable with this assessment was actually kind of obvious. The Carrington Event happened in 1859. 1859 was before power grids, before the Industrial Revolution was fully complete, before electricity was anything more than a curiosity that wealthy people used to light their homes. The most advanced technology on the planet was the telegraph. Morse code, copper wire. It was about as far removed from our modern civilization as you could possibly get. So when the Carrington Event happened, When it overwhelmed the telegraph network and shocked operators and set papers on fire, it was terrible for the time, but it was not civilization ending. It was not technology destroying. It was a major inconvenience to a world that did not depend on electricity for survival. That comfortable framing made a lot of sense. For 150 years, nobody had to worry. Part 4. The night the Earth became a battery. September 2nd, 1859, the night after the Carrington flare. All across the world, people were seeing something that most of them had never seen before, the aurora borealis. In the far north, auroras are common, but on this night the aurora was visible almost everywhere there was a clear sky. It was visible at the tropics. It was visible in places where the night sky barely ever shows the northern lights. In Havana, Cuba, observers at the observatory looked upward and saw the sky itself seem to be stained with blood. That is how they described it. The heavens appeared stained with blood and in a state of complete conflagration. In Kingston, Jamaica, the aurora was so bright that people wrote that it appeared as if there was a colossal fire on the earth itself, as though the entire ground was burning. In Honolulu, Hawaii, far from the Arctic regions where you would normally expect to see an aurora, observers noted quite a display of the aurora borealis occurring. In the Rocky Mountains, in what are now the western United States, gold miners were woken up by the light. They came stumbling out of their tents at 3 a.m, saw the brilliant auroral glow covering the sky, and assumed it was dawn. They thought the sun was rising. They started preparing for the workday in the middle of the night because the light was so brilliant. In the northeastern United States, people were not woken up by it. They were already awake, reading. Because the auroral light was bright enough to read a newspaper by. Not barely, not if you squinted, but clearly in normal readable light. Along the east coast the night was illuminated as if by gaslight. In the southern hemisphere, in the other direction of the world, the same thing was happening. The aurora australis was observed in Santiago, Chile and in Queensland, Australia. A global phenomenon. A planetary light show triggered by an explosion on the sun. But the visual spectacle, as astonishing as it was not the real story. The real story was what the aurora represented. It was the visible manifestation of something far more profound happening to Earth's electrical environment. When a CME arrives at Earth, it collides with Earth's magnetosphere, the shield of magnetic field that surrounds our planet. The impact is incredibly violent. The magnetosphere gets compressed on the sun-facing side and stretched out on the night side like a windsock caught in a hurricane. The magnetic field lines get twisted and tangled, and in that chaos, something happens that connects the upper atmosphere of the Earth to the surface itself. A circuit is completed. The Earth becomes part of an enormous electrical system. Imagine that you have a giant conducting sphere, the Earth, and you have a conducting layer high up in the ionosphere, about 100 kilometers above the surface. Normally, the electrical resistance between these two layers is very high. Electricity does not flow easily from the ionosphere down to the surface or vice versa. But when a CME arrives and the magnetosphere is disrupted, something changes. The electrical resistance plummets, the path becomes conductive, and the electrical currents flowing in the magnetosphere and ionosphere suddenly find a path to discharge through the Earth itself. The most remarkable evidence of this came from the telegraph operators, because the telegraph system at that time was the most sensitive electrical instrument that humanity had yet created. Telegraph operators sat at their desks with a key, tapping out Morse code through miles and miles of copper wire. The electrical current that flowed through that wire was tiny, just enough to make an electromagnet click. But it was measurable, it was controlled, it was understood. On the night of September 2nd, 1859, approximately 100,000 miles of telegraph lines fell silent. Nearly simultaneously, across the United States, across Europe, telegraph stations went dead. Operators were shocked, literally. They reported being knocked back from their desks by sudden surges of electrical current. The telegraph paper, the long rolls of paper that recorded the incoming signals, burst into flames. The current flowing through the wires was so high that the paper ignited. But then something truly extraordinary happened. Some telegraph operators, trying to figure out what was going on, decided to disconnect their batteries. See, a telegraph key needed a battery to operate. The battery provided the electrical power that would flow through the wire when the key was depressed. But on this night, some operators discovered that they could send messages without the battery. The key was working, the electromagnet was clicking, Morse code was being transmitted. But where was the power coming from? The answer was the Earth itself. The aurora-induced currents flowing through the ground, through the bedrock, were powerful enough to drive the telegraph. Between Boston and Portland, Maine, operators managed to maintain contact for approximately 2 hours using no battery at all, powered entirely by electrical currents flowing through the Earth's crust. In another case, a distance of 32 miles, operators communicated with no battery. Just the ground beneath them turned into a conductor by the disturbance in the magnetosphere. The instrumental data, when we look at it from our modern perspective, is staggering. The magnetometers at Kew Observatory recorded a DST value, which measures the strength of the disturbance, of approximately negative 401 nanoteslas. That means the magnetosphere was hit with such force that it disturbed the entire planet's magnetic field. But the magnetometer at Colaba Observatory in India recorded an even more extreme value of negative 1600 nanoteslas. And here is the thing that really shows how extreme this was. The measurement devices themselves failed. At Kew, the photographic recording pens went past the edge of the paper. The magnetic disturbance was so powerful that the instruments designed to measure it physically could not measure it. The pens just ran off the edge of the page. The disturbance was literally off the scale. The total energy released by the Carrington Event is estimated at around 2 × 10 to the 33rd power ergs. That is a number so large that it is hard to put into context. An erg is the unit of energy you have to use to even begin to describe something this big. The combined energy of all the atomic bombs ever tested by all the countries in the world over all of human history would not equal the energy in a single Carrington-level event. We're talking about something that dwarfs human destructive capability by orders of magnitude. And the flare itself, when calculated retroactively using modern techniques similar to what the University of Otago applied to the Halloween storms, is estimated to have been an X45 or possibly higher. So the Halloween storms of 2003, which everyone thought was the worst solar event of the satellite era, was approximately equal to, or possibly slightly smaller than the Carrington event. They were both in the same ballpark. They were both near the top end of historical solar violence. But here is what separates the Halloween storms from the Carrington event, in a way that should keep you up at night. The Halloween storms happened in 2003. In 2026, we recovered completely. Satellites are designed to be somewhat resilient to radiation. We have redundancy in our systems. We have protocols. We shut things down and ride out the storm. Some satellites were damaged, but we have replacements. The Edeos 2 that was destroyed was $1 billion loss, but Japan built another one. The communication blackouts were significant, but the world did not end. We adapted. We survived. The Carrington event happened in 1859. The world had no choice but to survive because there was nothing to lose except the telegraph network. But imagine for a moment what a Carrington-level event would do to a world that depends on electricity for almost everything. Not some things. Almost everything. The power grid, the internet, GPS satellites, the refineries that produce gasoline, the water treatment plants, the hospitals, the supply chains that bring food to cities. All of it runs on electricity. All of it depends on a power grid that was built with no understanding of extreme solar events. And the consequences are not abstract. Lloyd's of London, the insurance company that writes policies for catastrophic events, estimates that a Carrington-level solar storm hitting the planet today would cause between $600 billion and $2.6 trillion in damage. The National Academy of Sciences estimates it could be greater than $2 trillion. Not just the initial damage, but the cascading failures, the economic collapse, the infrastructure breakdown that would take years to recover from. Because the problem is not just that transformers would be destroyed. The problem is that replacement power transformers, the really large high-voltage transformers that are essential to the power grid, take between 1 and 2 years to manufacture. There is no surge capacity. There is no ability to rapidly replace them. If a Carrington event knocked out a few hundred of them simultaneously, which is what an analysis suggests would happen, the power grid would be crippled for years. For 153 years, that was the worst thing humanity had to worry about. A Carrington event. A disaster that could happen but probably would not happen again in our lifetime. Or maybe ever. It was the gold standard of bad things the sun could do. Scientists had measured the worst flare in recorded history. They knew the ceiling. They understood the limits. They could plan around it. And then, in 2012, a doctoral student in Japan found a piece of wood, and everything changed. Part 5. The Woman Who Read the Trees. So we have the Carrington event established as the worst-case scenario. For a century and a half, it sat at the top of the solar catastrophe pyramid. Carrington was the yardstick against which all other solar events were measured. If you wanted to talk about what the sun could do, Carrington was the answer. And then in 2012, a doctoral student in Japan picked up a piece of wood, and everything changed. Her name was Fusa Miyake, and she worked at Nagoya University studying annual growth rings in Japanese cedar trees. She wasn't specifically looking for evidence of ancient solar catastrophes. She was examining the carbon-14 levels preserved in tree rings as a way to understand cosmic ray intensity fluctuations throughout history. The basic principle is elegant. Trees absorb carbon-14 from the atmosphere as they grow, incorporated into the cellulose of each annual ring. Each ring, in essence, preserves a snapshot of the cosmic ray intensity for that specific year, locked in the wood. When cosmic rays strike nitrogen and oxygen atoms high in the atmosphere, they produce carbon-14. More cosmic rays equals more carbon-14. So by measuring the carbon-14 levels in each ring, you're essentially reading the history of solar wind strength and cosmic ray bombardment, year by year, century by century. What Miyake found when she examined the ring for 774 to 775 CE was something that made her stop and look at it again. The carbon-14 content had spiked, not by a little bit, not by the kind of oscillation that happens regularly from normal cosmic ray activity. The increase was approximately 20 times larger than ordinary cosmic ray variations. It was a 1.2% jump, the largest and most rapid rise in radiocarbon ever recorded in any tree ring ever studied. When she published her results in Nature in 2012, it sent a shockwave through the scientific community. Here's the thing about tree ring carbon-14 signatures. They're stable. They don't fluctuate wildly. The changes are usually small, gradual, reflecting the natural cosmic ray background. To produce a spike of that magnitude requires something extraordinary, something violent. The detective work that followed was like reverse engineering a crime scene using only wood. Multiple exotic hypotheses got proposed in the early days. Could it have been a nearby supernova, close enough to bathe Earth in cosmic radiation? Could it have been a gamma-ray burst, one of the most energetic events in the universe? Could a large meteorite have impacted the atmosphere, disturbing the ionosphere in ways that amplified cosmic ray production? These were serious suggestions from serious scientists because the spike was so anomalous that it seemed to demand an equally anomalous explanation. But then Brian Thomas at Washburn University and Adrian Mellott at the University of Kansas published a paper in Nature in 2013 that systematically worked through the probabilities. Supernovae and gamma-ray bursts, they showed, are rare enough that they couldn't produce events at the observed frequency. The math didn't work. The universe simply isn't flinging gamma-ray bursts at Earth on the timescales that would be required to generate multiple Miyake events over human history. So it wasn't that. The answer came from Ilya Usoskin, who works at the University of Oulu in Finland and is one of the world's leading experts on solar particle events. Usoskin did the calculations and came to a conclusion that actually made more sense. even though it was somehow even more unsettling. The 774 CE spike, he determined, had to have been produced by an extreme solar particle event, not from a distant star, not from the cosmos at large, from our Sun, specifically from a very strong solar flare, and not just strong, perhaps the strongest known. And here's where I want you to sit with this for a moment. We spent the last two parts talking about the Carrington Event. We discussed it like it was the ultimate expression of solar wrath, the worst-case scenario, the thing that should keep grid operators and government officials awake at night, the ceiling of what the Sun could do. The 774 CE event was 80 times more powerful. Let me say that again because it's important. The Carrington Event, which shut down telegraphs across the planet and created auroras so bright people thought the Sun was rising in the wrong part of the sky, was 80 times weaker than what happened in 774 CE. 80 times. The thing we were treating as the worst-case scenario was barely a scratch compared to what we now knew the Sun had done before. But Miyake's discovery raised an immediate question. Was this a one-time freak occurrence? A cosmic dice roll that came up snake eyes once and then never again? Or had it happened before? Was there a pattern? Were there other events hiding in the tree rings, waiting to be found? Part 6. Written in every tree on Earth. The answer came quickly. Other researchers began going back to their tree ring data with new eyes, armed with the knowledge of what to look for, and they found it everywhere. German oak trees showed the same spike in carbon-14 for the year 774 to 775. New Zealand kauri trees, genetically distinct species from the opposite hemisphere, thousands of miles away from Japan, showed the same spike. Russian trees, Finnish trees, American bristlecone pines, samples from all across the northern and southern hemisphere, all of them recorded the same event. Whatever had happened in 774 CE, it wasn't localized. It wasn't a regional phenomenon or an artifact of Japanese tree growth patterns or seasonal fluctuations. It was global. The verification came from multiple independent sources. Ice core data provided the smoking gun. Antarctic ice cores drilled from Dome Fuji showed an approximately 80% increase above baseline in beryllium-10 and corresponding spikes in chlorine-36, both isotopes that are produced when cosmic rays interact with the upper atmosphere. When cosmic rays increase, these isotopes increase. And the ice cores showed the same increase for the same year, 774 to 775 CE. The atmosphere itself had recorded what happened. The chemical signature of extreme cosmic ray bombardment was preserved in frozen water that had fallen as snow 1,200 years ago and accumulated in the Antarctic ice sheet ever since. There was even a historical record. A student named Jonathan Allen at UC Santa Cruz was studying the Anglo-Saxon Chronicle, those invaluable medieval documents that recorded major events in early English history. Around the year 774 CE, the Chronicle included an entry about a red crucifix after sunset. It was a curious note, vague enough to seem potentially mythological or religious rather than astronomical. But Allen made the connection that the broader scientific community had been too focused on tree rings and ice cores to consider. The red crucifix visible after sunset wasn't a religious vision. It was almost certainly a spectacular aurora borealis display, the northern lights, but on a scale so extreme that it produced visual phenomena that medieval observers described in the only terms they had available. A cross-shaped blood-red glow in the night sky. That's what a Miyake event looks like from the ground. That's what the sun's fury looks like when it's painting the sky. Picture the moment of discovery in your mind. A paleoclimatologist in Finland holds a cross-section of wood from a tree that died and fell into a bog over 1,000 years ago. The wood is so old that it predates most of European history, yet it's preserved perfectly in the anaerobic environment of the wetland. The scientist counts backward through the rings, one for each year, moving from the outer edge toward the centre. 50 years, 100 years, 200 years, moving back through time. and then reaching the ring for 774 CE, finding something anomalous, a signature, chemical evidence that something violent had touched the atmosphere that year. The carbon-14 locked in the wood tells a story that no human writing records, no historical document preserves. It's a scientific artifact, evidence carved into cellulose by cosmic radiation. And it's not just one tree, it's every tree. Across continents, north and south, oak and cedar and pine and kauri, species that diverged millions of years ago and evolved in complete isolation, yet every one of them records the same event. The 774 CE spike is written in the rings of every tree on Earth that was alive that year. The sun had done something so powerful that the chemical consequence was global and indelible. 1,200 years later, that violence still speaks from the wood. This wasn't a local event. It wasn't an anomaly in one tree or one region. It wasn't something that happened in one hemisphere and missed another. Every tree on the planet that was alive in 774 recorded the same thing. The sun had done something so powerful that the chemical evidence survived in wood for over 1,000 years, waiting to be read by scientists centuries later who would develop the techniques to decode it. And once scientists knew what to look for, once they had the signature, they started finding more of them. The catalogue of invisible catastrophes was beginning to emerge. Part 7. The Catalogue of Invisible Catastrophes. The systematic search for Miyake events expanded across the world. Different research teams, different samples, different methodologies, all converging on the same question. How many times had this happened? If the 774 CE event was real, were there others? And the answer, it turned out, was yes. Multiple times. In the last 15,000 years, the evidence shows our sun has been capable of something that mainstream solar science had considered essentially impossible until it was found written in the rings of ancient wood. Let me walk you through the catalogue. These are confirmed or strongly supported Miyake events, stretching back through human and pre-human history. 774 to 775 CE remains the most studied. That 1.2% jump in carbon-14, that 80% spike in beryllium-10, the red crucifix in the night sky. The event was somewhere between 40 and 100 times stronger than the strongest solar particle event ever recorded in the instrumental era, the one from February 23, 1956. By comparison to the Carrington Event, it was approximately 80 times more powerful. This is the baseline. This is what we're building from. 993 to 994 CE shows another significant spike in carbon-14. Researchers confirmed it in bristlecone pine samples, same era as the Carrington Event geologically speaking, within spitting distance on a timescale of centuries. Medieval civilization recorded this one happening during the reign of Otto III in the Holy Roman Empire. There's a historical note about a particularly bright aurora. But again, like with the 774 event, the civilization that experienced it was pre-industrial and left no damage record. 664 to 663 BCE was initially dated only approximately circa 660 BCE, based on earlier data. But in 2024, Irina Panuskina at the University of Arizona Laboratory of Tree Ring Research refined this date, publishing in Communications, Earth and Environment. She detected the event in Arctic larch tree rings from Siberia. That same year, around 2,674 years before our current moment, the Sun reached out and struck Earth with an extreme solar particle event that the Arctic larch trees recorded perfectly. 5,259 BCE. This one is particularly interesting because it was detected not in tree rings that were still part of a living tree, but in waterlogged wooden building remains at the Neolithic site of Dispilio in Greece. This allowed archaeologists to do something they'd never been able to do before: absolutely pinpoint the date of an ancient Neolithic structure to a single calendar year. This wood had been dated roughly archaeologically to the Neolithic period. But the carbon-14 spike gave it a precise date, 3,100 years before the Carrington Event. The Sun was doing this while humans were still in the Neolithic, still on the cusp of developing agriculture. 7,176 BCE appears in tree rings and in preliminary ice core data. This is at the edge of the Holocene, in the early days of the current interglacial period, and then 12,350 BCE. This is the largest known Miyake event. Not the biggest we think the Sun might be capable of. The biggest one that's actually confirmed in the geological record. It was discovered in ancient trees from eroded banks of the Druze River near Gap in the southern French Alps. Published in 2025 in Earth and Planetary Science Letters. This event was 18% stronger than the 774 CE event. That means it was approximately twice the combined size of the 774 and 993 events together. It was over 500 times more intense than the solar storm we experienced in May of 2025. It is the only known extreme solar event outside the Holocene, the first to reach back into the Pleistocene, and it happened during the last ice age, when humans were few, scattered, and technologically primitive. If it happened tomorrow, the world would burn differently. There are additional candidates requiring more confirmation. 5,410 BCE, 1,052 CE, 1,279 CE. So we're looking at somewhere between 9 and 10 confirmed or probable Miyake events in the last 15,000 years. Do the math on the frequency. 15,000 years divided by 9 events gives you approximately 1 Miyake event every 1,667 years. But the distribution isn't even. Some estimates suggest they could be as frequent as once every 400 years. Ice core data suggests once every 500 years. That translates into roughly a 1% probability of a Miyake event occurring in the next decade. 1 in 100. Not negligible. Not even close to negligible. Each new discovery pushed the ceiling higher. The Carrington Event wasn't the limit of what the Sun could do. It wasn't even close to the limit. It was barely a footnote in the history of solar catastrophes, and the events kept getting bigger the further back we looked into the geological record. Every time scientists thought they'd found the maximum, new evidence forced them to revise upward. That's the pattern. That's the lesson written in ancient wood and ancient ice. So here's the question that follows naturally. We know the Sun has done this before. We know it could do it again. We know the frequency suggests it probably will. So what would happen if one of these events, not the Carrington event, but a real Miyake event, an 80 times stronger Miyake event, or better yet, the 12,350 BCE monster that was twice as strong as the rest, struck Earth right now? What would our civilization look like in the aftermath? Part 8. A civilization built on glass. The answer depends on a fundamental asymmetry that we should probably think about more than we do. The 774 CE event was by every measure the most powerful confirmed Miyake event in the Holocene. It was staggering in its energy release. It was global in its reach. Its chemical signature is imprinted in every tree on Earth from that era. And when it happened, what civilization recorded about it amounted to a note about seeing a red cross in the sky. There was no documented collapse, no accounts of widespread infrastructure failure, no records of societal disruption beyond the natural occurrence of a spectacular aurora. A medieval scribe saw something beautiful and unexplainable and wrote it down, and that was the extent of the damage to an entire global civilization. That same event hitting Earth in 2026 would be catastrophic on a scale that's genuinely difficult to contemplate without sounding hyperbolic. Start with the immediate effects. Power grids across entire continents would fail. The geomagnetic disturbance would induce currents in transmission lines fast enough and powerful enough to damage transformers, not just trip breakers, damage them, break them. The extra high voltage transformers that distribute power to cities and regions are custom-built pieces of infrastructure. They cost millions of dollars each. They take 1 to 2 years to manufacture. The United States maintains spare inventory for less than 10% of the installed base. So if you lose 30% of the transformers across North America in a single geomagnetic event, you're looking at a supply crisis where demand far exceeds manufacturing capacity by an order of magnitude. While you're waiting for new ones to be built, entire regions of the continent are without power. Satellites would be knocked out. Geosynchronous satellites, which provide long-distance telecommunications, would fail. Low Earth orbit satellites would fail. The Van Allen belts would be energized to lethal levels temporarily. Any satellite in orbit would experience increased particle radiation. And to give you a sense of what increased particle radiation actually means in practical terms, consider the May 2024 G5 geomagnetic storm. That was far, far below the scale of a Miyake event. It was roughly at the Carrington Event level, maybe a bit weaker. That event alone caused approximately 40 Starlink units to be lost due to increased atmospheric drag. 40 satellites out of a constellation of thousands. A Miyake event would be 100 times more severe. You're looking at catastrophic satellite loss. GPS would disappear. This seems abstract until you realize how dependent modern agriculture is on GPS-guided farming equipment. During the May 2024 storm, GPS disruptions during critical spring planting periods cost American farmers approximately $500 million in lost productivity. That was from a storm significantly weaker than what we're discussing. A Miyake event would eliminate GPS globally for an extended period. Financial systems that depend on GPS timing for high-frequency trading would stop functioning. Aviation navigation would be compromised. Military infrastructure would be compromised. Telecommunications networks would collapse. Mobile phone networks would fail. The internet backbone relies on fiber optic cables, and while those are more resistant to geomagnetic storms than copper infrastructure, the systems that route and amplify signals through the internet depend on electronics that would be damaged or overwhelmed. Most of the modern interconnected world would go dark. Now, here's the part that actually keeps grid operators and emergency planners awake at night. Recovering from this wouldn't be like recovering from a hurricane or a regional blackout where you're bringing systems back online in days or weeks. The bottleneck is the transformers. You can't build new ones fast enough. You can't reroute power because the transformers that would handle the rerouting are either damaged or already at capacity. You're looking at a global power crisis measured in years, not days. Food production would collapse because modern agriculture depends on mechanization and GPS and irrigation systems powered by electricity. Water treatment would fail. Medical infrastructure would collapse. Communications would disappear. The cascading failures would be virtually impossible to contain because every major system we depend on is interconnected and reliant on the ones around it. So what's the economic cost of that? Lloyd's of London estimates a Carrington-class event would cost between $600 billion and $2.6 trillion. That's the cost to the global economy. The National Academy of Sciences puts the figure higher, greater than $2 trillion. For a Miyake event that's 80 to 100 times more powerful, you'd multiply those figures accordingly. We're looking at something in the range of tens of trillions to hundreds of trillions of dollars. We're looking at economic damage that would dwarf any natural disaster in recorded history. We're looking at a genuine existential threat to modern civilization. And here's the cosmic irony that really gets under your skin when you think about it. The most powerful confirmed Miyake event in the current geological period, the one from 774 to 775 CE, hit a planet with almost nothing to destroy. It produced a spectacular aurora, and that's what people remember about it. A red cross in the night sky. An unexplained phenomenon. A moment of wonder. Because the civilization that experienced it was built on wood and stone and muscle power. It was vulnerable to many things, but not to geomagnetic induction in power transmission lines. The sun's fury passed through like a ghost. We have built a civilization uniquely vulnerable to something that has already happened. Not once, not twice, at least 9 times in the last 15,000 years. Maybe as often as once every 400 years. probably at least once every 2,000 years, and the most powerful one we know of, the 12,350 BCE monster that was twice as strong as anything else in the Holocene, hit a planet with nothing to destroy, with no power grids to fail, no satellites to lose, no GPS systems to go dark, no global supply chains to collapse. If it happened tomorrow, it would find plenty to destroy. We exist in a window of solar calm. The geological record proves this. We've been fortunate enough to have built our technological civilization in an era when the sun, for reasons we still don't fully understand, has been relatively quiet. But the window is not guaranteed to last. The history of the sun, as written in trees and ice, shows us that occasionally it opens a door and lets something terrible through. But even the Miyake events, as terrifying as they are, might not be the top of the ladder. Because while Fusa Miyake was reading tree rings in Japan and building the case for extreme solar particle events, another group of scientists was watching other stars. A space telescope called Kepler was performing the first large-scale survey of exoplanets around distant suns, and what it found suggested that our sun, that we've been treating as the dangerous one, might be capable of something even worse, something that makes a Miyake event look like a warning shot. Part 9. Stars Like Ours. In 2012, the same year Miyake published her findings, something else happened in the scientific literature that should have gotten far more attention than it did. A team of astronomers led by Hiroyuki Mihara published a landmark study in Nature that took everything we thought we knew about solar flares and quietly, methodically, expanded the boundaries of possibility. They weren't looking at our sun directly. Instead, they pointed the Kepler Space Telescope at 83,000 sun-like stars and monitored them for 120 days, watching their light curves the way a cardiologist watches a heart monitor. Most of those stars were boring. They just sat there, steady and reliable, their light output varying by less than a fraction of a percent as they rotated. But on a handful of them, something extraordinary happened. The light spiked. Suddenly, dramatically, a star would briefly double its brightness, then fade back to normal. These were superflares, and Kepler found 365 of them hiding in that data. Now, I need you to really sit with what this means. Mihara's team detected eruptions releasing between 10 to the 33rd and 10 to the 36th ergs of energy. Let me put that in perspective. A normal solar flare, the kind we observe all the time, releases between 10 to the 28th and 10 to the 32nd ergs. So these superflares were releasing 10 to 10,000 times more energy than a typical flare. The Carrington Event, which until that moment we treated as this once-in-many-centuries catastrophe, released something like 10 to the 33rd ergs. These superflares weren't just bigger, they were in a different category entirely. But here's what made Mihara's paper truly unsettling. Most of the superflares occurred on rapidly rotating stars, the young frenetic kind spinning around their axes multiple times a month. But Mihara identified 14 superflares on slowly rotating sun-like stars, with rotation periods greater than 10 days. These stars had the same temperature as our sun, the same size, the same age. They were stellar doppelgangers, and they were producing eruptions that seemed impossible, according to everything we thought we understood about stellar magnetic dynamics. When you actually look at the Kepler data, it's visually arresting in its mundanity. You see this progression of star after star, thousands of them on the screen, their light curves rendered as straight lines month after month. Flat, steady, reliable. The kind of stars you'd want to build a civilization around. And then occasionally, without warning, there's this sudden spike, a star's output jumping by 20, 30, 50% for hours before plummeting back down. It happens maybe a few times across the entire data set, but it happens. And these aren't the exotic objects you'd expect. They're not dying stars or young stellar nurseries or gravitationally tortured systems. They're ordinary stars. Stars that could have planets. Stars that could have civilizations. Mihara's initial estimate was cautiously phrased, as scientific estimates tend to be. Based on the frequency of superflares he observed on slowly rotating sun-like stars, he calculated that eruptions of 10 to the 34th ergs or greater likely occur approximately once every 800 years on such a star. Sit with that number for a moment. 800 years. That's not a geological timescale anymore. That's a human timescale. That's the span of multiple civilizations. That's the kind of number that should have made headlines, and yet somehow it didn't quite penetrate the public consciousness the way it should have. Remember the escalation ladder? We had normal flares at the bottom. Then we climbed up to the Carrington Event, which we thought was the maximum expression of what the sun could do. We felt pretty secure on that rung, honestly. And then Miyake events came along and yanked the ladder upward by a factor of 80 to 100. We recalibrated. We told ourselves that this was the real ceiling, the highest rung on the ladder, and then Mihara published his paper, and Kepler showed us that stars identical to our sun were producing eruptions that made even the Miyake events look modest. That made the Miyake events look like the normal operating procedure for these catastrophic outbursts. But here's the thing about that study that should have made the alarm bells even louder. The Kepler observations spanned only 120 days. 120 days out of the billions of years those stars have existed. It was like watching a security camera outside a building for 4 months and then trying to estimate how often earthquakes occur. You're going to get biased statistics. You're going to miss rare events. Mihara himself knew this. The whole field knew this. And when another team decided to go back to the Kepler archive and analyse not just the data from those first 120 days, but the entire 4-year Kepler mission, the numbers started looking even more alarming. Part 10. Once per century. A researcher named Yuta Notsu at the University of Colorado Boulder led a team that essentially said we need to look at this more carefully. They took the full 4-year Kepler dataset, combined it with spectroscopic observations from the Apache Point Observatory, and cross-referenced everything with precise distance measurements from Gaia DR2 parallax data. This wasn't just looking at light curves anymore. They were studying the actual magnetic properties of these stars, their rotation rates, their age, their composition. They were building a complete picture of what kinds of stars produce superflares. When the analysis was complete, Notsu's team had identified 2,889 superflares occurring on 2,527 sun-like stars. These were selected from 56,450 stars that were observed throughout the mission. The sample size had just gotten exponentially larger and more robust, and when they recalculated the frequency, using all this new data, the estimate for how often a superflare of 10 to the 34th erg or greater occurs on a sun-like star came out to approximately once per century, not once per 800 years, once per century. That's a 10-fold increase from Mihara's original estimate. That's the difference between a rare historical event and something that could happen in your lifetime. Notsu was careful to note the uncertainty, the error bars, the caveats. But he also said something that cuts through all of that. There is some possibility, he stated, that we could experience such an event in the next 100 years or so. He didn't say it would happen. He said it's possible. He quantified that possibility at roughly 1 in 100. Those aren't great odds when the stakes are what we've been discussing. Of course, not everyone in the solar physics community accepted this conclusion quietly. The scientific debate that emerged is actually worth understanding because it reveals something important about how we evaluate risk when we're operating in the realm of incomplete information. A group of researchers led by Balazs Schaefer and a couple of collaborators named King and Delianis published a paper in the Astrophysical Journal in 2000 arguing something different. They had analysed 9 historical superflare stars and proposed a hypothesis. Superflares, they suggested, occur preferentially on stars that have hot Jupiter companions, these massive gas giants orbiting extremely close to their host stars. The gravitational tidal heating from these companions promotes unusually strong magnetic activity. And here's the key part. The Sun doesn't have a hot Jupiter. We looked for one. We didn't find it. Their prediction was straightforward and unambiguous. Our Sun will never produce superflares. Mihara himself had noted another complication. The stars that produce superflares seem to have unusually large star spots, these dark blemishes on the stellar surface caused by intense magnetic activity. The modern Sun's star spot distribution doesn't really match what we see on superflare stars. Modern measurements suggest our Sun's star spots are relatively typical, which is consistent with Schaefer's view that we're not a superflare candidate. But Notsu's evidence suggested something else. Using spectroscopic analysis, he showed that slowly rotating Sun-like stars do indeed produce superflares, regardless of whether they have hot Jupiters or unusually large star spots. The statistical modelling supports the approximately 1 in 100-year probability. The Sun's current parameters don't absolutely preclude superflares, they just make them seem unlikely based on what we observe today. Here's where it gets genuinely uncomfortable. There's a fundamental disagreement between two different sources of evidence. One group of scientists looking at the stellar population through Kepler says the Sun could definitely produce a superflare, and we should assign a meaningful probability to it happening within our lifetime. Another group looking at the detailed physics and properties of our Sun says it's very unlikely or impossible. And then there's a third source of evidence, the one that's been preserved in the geological record, that sits somewhere in between and confirms something deeply troubling. The tree rings and ice cores don't lie. They show evidence of superflare-class events in Earth's past, just not as frequently as Kepler's statistics would predict. If you take Kepler's frequency and assume it applies directly to our Sun, you'd expect to find multiple superflares per millennium in the radiocarbon record. What we actually find is closer to 1 every few thousand years, maybe less. So there's this gap, this discrepancy between the statistical predictions from studying other stars and the actual history of what happened to Earth. Scientists have proposed 3 main explanations for this gap. The first is that not all superflares send a significant flux of charged particles toward Earth. Depending on the geometry of how the solar wind interacts with the flare, the particle stream could miss us entirely. The second explanation is that Kepler has a detection bias. Maybe the instrument is particularly good at finding superflares on certain types of stars and misses them on others. The third explanation, the one nobody really wants to be true, is that the Sun's intrinsic superflare rate is genuinely lower than the population average of Sun-like stars, meaning we're somewhat luckier than average, but that luck isn't guaranteed to last. This is the uncomfortable position we're in. One legitimate scientific camp says the Sun cannot produce a superflare. Another says the math suggests it might, maybe once a century. A third camp, looking at the Earth's history, confirms that superflare-class events have occurred but less frequently than the stellar statistics would predict. So the honest answer to the question, can our Sun produce a superflare, is that we don't know. We have different lines of evidence pointing in different directions, and everyone agrees that if we're wrong about how often they occur, the consequences are so severe that being wrong in an optimistic direction would be the worst kind of luck. Part 11. The Biological Threshold. Let me ask you a question you've probably been avoiding thinking about. What actually happens if a full superflare hits Earth? Not to technology, not to our power grids or satellites or supply chains, to us, to biology, to the living systems that have spent 4 billion years adapting to this environment. Because a superflare crosses a threshold that no other solar event reaches. It stops being primarily a threat to our civilization and becomes a threat to life itself. Start with the ozone layer. That thin shell of 3 oxygen molecules sitting between 15 and 35 kilometers up has been our sunblock for nearly the entire history of complex life. It absorbs ultraviolet radiation before that radiation can reach the surface. Modelling studies from multiple research groups examining what happens to ozone under the enhanced particle flux from a superflare have produced estimates that range from 5 to 50% ozone loss, depending on how intense the flare is and what kind of particle spectrum it produces. That's a huge range, I know. The difference between those two numbers is the difference between a serious problem and a catastrophe. But let's think about what even the lower end of that range means. A 5% reduction in total column ozone might sound manageable, but it compounds with seasonal variations and latitude-dependent factors. In many parts of the world, it would still produce significant increases in surface ultraviolet radiation. Now look at the upper end, 50% ozone loss. If you're in the northern hemisphere and it's summer and you're standing in New York, the effective UV index on a clear day would be approximately equivalent to standing on the equator at solar noon with no atmosphere at all. None. Skin burns in minutes, not hours. Unprotected skin becomes blistered and unusable in maybe 5 minutes. Crop plants that have never evolved to handle this level of radiation start dying within days. The phytoplankton that form the base of the ocean food web, the single-celled organisms that produce most of the world's oxygen, those die too. Entire ecosystems that have been optimized for a particular UV level suddenly find themselves in an environment they've never experienced in their evolutionary history. But there's something else, something that most people don't realize when they think about superflare damage. The particles that cause ozone depletion aren't the only threat. Mihara's 2012 paper documented superflares, but follow-up studies looked at the energies of the particles that these flares produce. A paper published in Science Advances in 2021 examined the relationship between superflares and the maximum energies of particle emissions associated with them. Superflare-associated coronal mass ejections can generate particles reaching maximum energies of 50 billion electron volts. 50 giga-electron volts. Compare that to typical solar flares, which produce particles at energies up to maybe 1 giga-electron volt. This is 10 to 100 times more energetic, and it matters because high-energy particles can penetrate further into the atmosphere. They reach the equator, they penetrate to the surface, they deliver lethal radiation doses without requiring ozone depletion as an intermediary. In combination, these effects are multiplicative rather than additive. The ozone destruction allows enhanced ultraviolet radiation through. The high-energy particles deliver direct radiation dose. The duration matters too. Depending on the strength of Earth's geomagnetic field at the time, recovery could take anywhere from 1 year with a strong magnetosphere to 6 years with a weakened one. That's 6 years during which ultraviolet levels remain elevated, during which UV-sensitive organisms struggle to survive, during which agricultural systems are disrupted, and biological productivity across the entire planet stays depressed. The infrastructure damage is almost a secondary concern at that point, but it's worth quantifying anyway. Complete satellite destruction, total grid collapse across hemispheres, economic costs measured in tens of trillions of dollars. In the United States alone, an estimate placed the population affected by total blackout at approximately 66%, with an economic cost of $41.5 billion per day for the duration of the outage. That's just the United States, just the economic disruption. It doesn't account for the biological impact. A study published in PNAS in 2024 examined the ozone depletion effects more carefully, focusing on the interaction between the particle flux from a superflare and the strength of Earth's geomagnetic field. The researchers found that under strong geomagnetic field conditions, ozone loss was at the lower end of the range. But if a superflare occurred during a period of weakened geomagnetic field, the loss could be at the upper end or even exceed it. And here's what makes that particularly unsettling. Earth's geomagnetic field strength isn't constant. It varies on 1,000-year timescales, and occasionally, roughly every 200,000 years, the field undergoes a complete reversal, flipping from north to south. During these reversals, which can take anywhere from 1,000 to 10,000 years to complete, the field strength drops to perhaps 25% of its normal value. If a superflare occurred during a geomagnetic reversal, you wouldn't just be looking at 50% ozone loss. You'd be looking at the upper range of theoretical predictions. You'd be looking at an event that could trigger ecosystem collapse across significant portions of the planet. Let me reconstruct the full escalation ladder for you now that we have all the pieces. A normal solar flare, the kind we observe all the time, releases 10 to the 28th to 10 to the 32nd ergs of energy. These are occasional, produce nice aurora displays, and are generally annoying for satellite operators but not catastrophic. An X10 class extreme flare, one of the most intense flares we've ever measured, releases approximately 10 to the 31st ergs, still within the normal range of solar variability. The Halloween storms of 2003 came close to this level. Now climb up to the Carrington Event, the one from 1859 that we've been using as our baseline for disaster. That event was probably an X40 or X45 class flare, releasing somewhere in the range of 10 to the 32nd to 10 to the 33rd ergs. Our entire modern understanding of solar catastrophe was built on this event. Then came the Miyake events, the ones we discovered through careful radioisotope analysis. The Miyake event of 774 CE released 10 to 100 times the energy of the Carrington event, so somewhere in the range of 10 to the 34th ergs. And there's evidence for an even larger Miyake event around 12,350 BCE that released 18% more energy than the 774 event. So we're still talking 10 to the 34th ergs, but at the high end of that range. And then, above all of this, exist the theoretical superflares that Mihara and Notsu observed on other Sun-like stars, 10 to the 34th to 10 to the 36th ergs, 100 to 10,000 times the energy of the Carrington event. A superflare of 10 to the 35th ergs would be 500 times the Carrington event. A superflare of 10 to the 36th ergs would be 5,000 times the Carrington event. These aren't just bigger events on a linear scale. They're events that operate according to different physical rules entirely. We started this entire journey by talking about the sun's surface, about those convection cells the size of Texas churning up heat from the interior, about the magnetic field lines that thread through the interior and emerge as twisted loops storing energy like rubber bands wound tighter and tighter and tighter. And now you can see what happens when those rubber bands don't just snap, when they don't just break under the strain of stored energy. A normal flare is the snap, the sharp release of energy stored in one localized region. The Carrington event was a violent break, a more complete disconnect and reorganization of the entire global magnetic field structure. Miyake events are the system failing more comprehensively, with larger regions of the sun's magnetic field undergoing sudden restructuring and releasing energy on a scale we haven't witnessed in the history of human civilization. And a superflare is the sun doing something that no human being has ever seen, something that the written record and the telescope records and the satellite records have never captured. But that happens to sun-like stars on what the Kepler data suggests is a meaningful timescale. There's a particular date I need to tell you about, July 23rd, 2012, because on that day, the sun actually fired a direct shot at us, and it missed by exactly 1 week. This is the part that keeps astrophysicists up at night, because it shows us exactly how close the window of opportunity really is. Part 12, the shot across the bow. Now, here's where things shift from theoretical to uncomfortably real. In July of 2012, the sun did something that would have changed human history, and almost nobody noticed at the time. On July 23rd, 2012, the sun produced a coronal mass ejection that was Carrington class in every single measurable way. Let me be precise about what that means, because the details matter here. The ejection was so powerful that when Daniel Baker from the Laboratory for Atmospheric and Space Physics analysed it after the fact, he published his findings in a journal called Space Weather in December of 2013. Baker calculated what the geomagnetic disturbance index would have been if this ejection had hit Earth. The DST value, that's the measure we use to rate the strength of geomagnetic storms, came out to approximately negative 1200 nanotesla. That matches or exceeds the Carrington event. Baker himself stated it directly. In my view, the July 2012 storm was in all respects at least as strong as the 1859 Carrington event. Not weaker, not comparable, as strong. But here's the crucial detail that makes this a near miss instead of a catastrophe. When the ejection happened, Earth was not in its path. We missed it. The timing was such that when that column of plasma reached Earth's orbital distance, our planet was somewhere else entirely. We were protected by nothing more than the rotational mechanics of two bodies moving through space. 1 week earlier, and the story would be different. 1 week, and the sun would have fired directly at us. Now, you might think that a Carrington-class ejection would have come from a similarly massive solar flare. That's the intuitive assumption. Bigger flare, bigger danger. The physics doesn't work that way. The originating flare was rated at x 2.5. That's significant, but it's nowhere close to the Carrington Event's estimated x 45. The flare itself was relatively modest. What made the ejection so catastrophic was something more subtle. The CME was actually 2 separate eruptions only 10 to 15 minutes apart, and they merged into a single unified structure. And 4 days before that, there had been another CME that cleared the interplanetary medium, essentially sweeping a path through the plasma that normally slows these things down. When the July 23rd ejection arrived, it hit a clear corridor. Physics stacked on top of physics, chance stacked on top of chance. This is the part that doesn't fit neatly into our narrative of understanding and control. The flare classification system, the one we use to categorize solar events on a scale from A class to X class, doesn't actually predict geomagnetic impact. A modest x 2.5 can produce a Carrington equivalent storm. We can measure the flare directly. We can calculate the solar wind properties, but predicting whether Earth will be hit and how hard still has elements of luck built into it. And that luck ran out once already this century, in the worst possible way. We got lucky. Now let's talk about what has actually happened in the decades since the last Carrington event. Let's ground this in events we can point to, storms that hit Earth and did measurable damage. In 1989, the Quebec blackout, a geomagnetic storm with a DST value of negative 589 nanotesla, caused a complete power grid failure across Quebec. 6 million people lost electricity for 9 hours in the middle of a cold snap. The infrastructure damage was modest because the storm wasn't particularly strong, but the cascading effect through a modern electrical network was stark and immediate. Then we move forward to the Halloween storms of 2003. A Carrington equivalent flare classified X45, the same magnitude as the original Carrington event. The resulting geomagnetic storm had a DST of negative 401 nanotesla. Not as powerful as the Carrington event would have been, but significant. And the damage list included the destruction of the Adeos 2 satellite, a joint Japanese-US Earth observation platform, lost to radiation damage. The satellite cost approximately $1 billion. 38 astronauts were in orbit during the storm, the crew of the International Space Station and a shuttle mission. They huddled in the lower decks, in the parts of the ISS shielded by water and equipment, and waited for the radiation to pass. Then we jumped to May 2024, a G5 geomagnetic storm, the highest category on our scale. The DST value was negative 412 nanotesla. This storm destroyed 40 Starlink satellites, just erased them. But it also revealed something that doesn't make the news as much: the global loss of accuracy in GPS farming systems across the hemisphere. Farmers use GPS to guide autonomous tractors, to apply fertilizer and pesticides in precise patterns, to measure yield. When the ionosphere gets hammered by a geomagnetic storm, those signals degrade. The cascading agricultural loss was somewhere greater than $500 million. Not in actual damage to crops, but in precision lost, in time wasted, in inefficiency that ripples through modern agriculture. And here's the thing that I keep coming back to. These events are not theoretical. They are not hypothetical. They happen. We have watched them happen. We have measured the damage. We have counted the money and the lost infrastructure and the hours without power. And all of these events, Quebec, Halloween, May 2024, were dwarfed by what nearly happened in July 2012. I want to make something very clear because I think it matters. We're not talking about something that might happen in some distant future. We're not talking about a scenario so unlikely that we can comfortably ignore it while we worry about other things. We're talking about something that nearly happened 12 years ago. In geological time, 12 years is nothing. It's a blink. It's a measurement error. We nearly got hit by an extinction-level capability event in 2012, and the only reason we didn't is that Earth was not where the Sun was aiming. If that CME had erupted 1 week earlier, you might not be watching this video right now, not because you wouldn't exist, you would exist, but because the infrastructure that delivers this video to you might still be recovering. The cellular networks might still be rebuilding, the power grids might still be stabilizing, the satellites might still be falling out of orbit, and everyone making content like this would be doing something more immediately necessary. So here's where we shift, because there is this whole other layer to solar science that I think is worth exploring, and it's not the mainstream science that we've been covering. It's the corner of the internet where people have taken the real data we've discussed, the tree rings, the superflares, the near-miss of 2012, and built much bigger narratives on top of it. And I think it's worth looking at, not because these ideas are right, but because understanding why they're wrong actually makes the real science even more impressive. Part 13. The Conspiracy Corner. There is a former lawyer named Ben Davidson who runs a YouTube channel called Suspicious Zero B Servers. He has accumulated a significant following by arguing that the Sun undergoes periodic catastrophic events called micronovas, and that these events follow a cycle of approximately 12,046 years. Davidson's thesis is that we are currently approaching the next micronova event, which he predicts could occur around 2046. He points to ice core data that shows anomalies he interprets as fingerprints of past micronovas. He references a spike at the end of the last ice age, around 9,700 BCE, which he claims represents an event 40 times the power of the Carrington Event. He also extensively references a book called The Adam and Eve Story, written in 1963 by a man named Chan Thomas. The book was classified by the CIA and later declassified in 2013, which Davidson uses as evidence that the government was suppressing knowledge of a catastrophic solar event. Now let's work through this carefully. Micronovae are real. That's the thing that makes this theory superficially compelling. Micronovae are actual astronomical events. They happen. They're just not happening on our Sun, and probably never will. Micronovae occur exclusively on white dwarf stars in binary systems, dead stellar cores that are pulling material from a companion star. The accreted hydrogen fuses in a thermonuclear runaway on the surface. It's a real thing. It's just happening somewhere else to a different kind of star. Our Sun cannot micronova because of a series of fundamental problems. First, our Sun is a main sequence star. It's a hydrogen fusing star in the prime of its life. Micronovae only happen on white dwarfs. When our Sun dies, in about 5 billion years, it will become a white dwarf. But it won't be in a binary system where it can pull material from a companion. Second, even if it were in such a system, the magnetic field of the Sun is the wrong order of magnitude. The Sun's magnetic field at its peak reaches about 4,000 Gauss. White dwarfs have magnetic fields sometimes measured in billions of Gauss. Third, there is no known mechanism in stellar physics that would produce a periodic cycle of 12,046 years. That number doesn't correspond to any known stellar oscillation or magnetic cycle. It's been reverse engineered from mythology and ancient text, not derived from physics. As for the Chan Thomas book, The Adam and Eve Story, it's a work of speculative fiction written in 1963. It describes a polar shift, a catastrophic transformation of civilization. It's imaginative, but it's not science. The book was classified by the CIA, yes, but the CIA classified all sorts of things during the Cold War. Classification doesn't mean suppress truth. It often just means it was written during a particular era when documents got classified routinely. The declassification of this book proved nothing except that the government had decided it wasn't a national security risk anymore. But here's the thing that makes me want to engage with these ideas seriously, even as I'm explaining why they don't hold up. The real solar science is so much more impressive than the conspiracy version. The data doesn't need micronovae to be terrifying. The data already shows us that the Sun is capable of things we have never witnessed in recorded history. Now, there's another layer to this, what we might call the ancient civilization reset theory. Graham Hancock, in his book Magicians of the Gods, argues that Miyake-class solar events catastrophically reset advanced ancient civilizations. He proposes that there was a sophisticated Ice Age civilization that was destroyed around 12,900 years ago by a massive solar outburst. The geologist Robert Schoch has suggested that the Younger Dryas, a period of rapid cooling that happened about 12,900 years ago, was caused by an enormous solar event rather than by comet impact, which was the mainstream hypothesis for a while. Now, the Younger Dryas is real. It happened. Temperatures dropped rapidly, and it had serious consequences for early human societies. The question is what caused it. And here's where the evidence becomes really important. We have one test case for what a Miyake-class event, an event 80 to 100 times more powerful than the Carrington event, actually does to civilization when it happens. That test case is the year 774 CE. In 774 CE, there was an enormous Miyake event. We know this from carbon-14 and beryllium-10 isotope spikes in tree rings worldwide. The event was 80 to 100 times more powerful than the Carrington event. If these events were capable of resetting civilizations, then 774 CE should show clear evidence of it. The archaeological record should show a disruption. Settlements should be abandoned. Writing should stop. Trade networks should collapse. Instead, we see basically nothing. Archaeological continuity before and after. No gap in the material record, no evidence of sudden societal breakdown. Why? Because the mechanism is wrong. A Miyake event causes geomagnetic storms, and geomagnetic storms cause problems for electromagnetic infrastructure. Pre-industrial societies didn't have electromagnetic infrastructure. They had bronze and stone and agriculture. You can disrupt a power grid with a geomagnetic storm. You can't disrupt a pre-industrial civilization with one, because the civilization isn't built on systems vulnerable to geomagnetic disruption. So 774 CE happened, and the next day people farmed and built and traded exactly as they had before. The only people who would notice a Miyake event in 774 CE would be someone with sensitive magnetometers, and those wouldn't be invented for more than 1,000 years. The Younger Dryas itself had a very different cause. It was triggered by changes in Atlantic Ocean circulation. Meltwater from the retreating ice sheets destabilized the Gulf Stream. You can trace this through paleoclimatology. It's a well-understood mechanism, and it happened. But it's not caused by the sun. There was a hypothesis for a while that a comet impact triggered the Younger Dryas. The Younger Dryas impact hypothesis. That hypothesis is now dead. There are no craters. The purported nanodiamond evidence was debunked by a crystallographer named David Dalton, who showed that what the researchers had identified as nanodiamonds were actually fungal spores and insect fecal pellets. And the flagship paper supporting the hypothesis was retracted in 2025 for data manipulation. So that theory is off the table. As for the idea of advanced pre-Younger Dryas civilization, the archaeological record just doesn't support it. The Egyptian pyramids show a gradual evolution from mastabas to step pyramids, to bent pyramids to true pyramids. This is not knowledge transfer from a lost civilization. This is observable innovation. People trying different things, failing, learning, refining the technique. The same pattern shows up everywhere we look in the archaeological record. Agriculture developed independently in multiple places. Writing developed independently in multiple places. The sophistication of human culture increased gradually over time. There's no evidence of a reset, no evidence of suddenly recovering lost knowledge, no evidence of cyclic catastrophe. And I think it's important to note what some of these theories imply. The Society for American Archaeology put out a statement noting that Hancock's ideas echoed and promoted dangerous racist thinking. The implicit assumption being that indigenous peoples couldn't have developed their own sophisticated cultures on their own. The idea of a lost advanced civilization doing the developing, with later peoples inheriting scraps of that knowledge, carries an ugly implication about whose peoples were capable of innovation. That's not a scientific objection, but it's a historical and ethical one. Here's my take on all of this. I bring up these ideas not to mock anyone who finds them interesting. Some of them genuinely are fun to think about in the way that speculative fiction is fun. But the real science is actually more impressive than the conspiracy. We don't need micronovas to happen on the Sun. We don't need lost civilizations to make the solar data terrifying. The tree rings already did that. The tree rings show us that the Sun is capable of violence we have never seen in recorded history, on a timescale we can measure, on a planet that is our only home. That's enough. That's more than enough. And what makes it even more impressive is that we have figured this out not through suppressed government documents or declassified CIA files, but through the simple act of measuring carbon-14 isotopes in tree rings and comparing them to the written record of the Carrington Event. That's science. That's how you actually solve mysteries. So where does all of this leave us? We've climbed the full escalation ladder. We've gone from solar flares to the Carrington Event to Miyake events to superflares that dwarf all of them. We've seen what the conspiracy world makes of this data and what the data actually shows. We've looked at near misses and close calls and events that rewrote our understanding of what's possible. And now there's only one question left. It's the one that matters most. And it's also the one we have no good answer for yet. Part 14. The Sun doesn't know we're here. The gap is the thing that keeps me up at night. The gap between what we have watched and what the evidence says has already happened. And I don't think there's an easy way to close it. For the last 70 years, we have continuously observed the Sun. We have satellites. We have magnetometers. We have spectrographs and coronagraphs and instruments dedicated to nothing but watching what the Sun is doing at any given moment. In 70 years of continuous observation, we've never seen anything close to a Miyake event. We've seen big events. We've seen powerful flares and coronal mass ejections and geomagnetic storms that knocked out power grids and destroyed satellites. But we have never seen what the tree rings tell us has happened before. The tree rings say that Miyake-class events occur, on average, once every 1,000 to 2,400 years. That's not speculative. That's measured. That's counted. And the last confirmed Miyake event that we can identify in the tree ring record was in the year 993 CE. That was over 1,000 years ago. We're now in a gap. The longest gap in recent geological history. The gap where we happen to be living. Here's the question that sits underneath everything. Either these events are extremely rare, consistent with the frequency estimate we get from tree rings, or our observation window is simply too short to capture the full range of what the Sun is capable of. We have 70 years of data from a star that has been active for 4.6 billion years. We are extrapolating from a sample size so small that it would be laughed out of any statistics course. We are trying to build a predictive framework on data that represents 0.0000015% of the Sun's history. We're making predictions about behavior based on a sample that might not even be representative. And here's the thing that makes this worse. We don't even know what triggers a Miyake event versus a normal solar flare. We don't know what the difference is in the physical conditions that produces a once-a-1,000-year event instead of a once-a-year event. We have theories. We have ideas about magnetic reconnection and flux rope instabilities and things in solar physics that I could talk about for hours. But we don't have certainty, and we definitely don't have the ability to predict when the next one is coming. We also don't know whether the Sun is an unusually quiet star or a completely normal star that simply hasn't erupted in the way it's capable of erupting while we've been watching. When we look at other Sun-like stars in the galaxy, we see something called the Kepler terrestrial discrepancy. We see a factor of 10 disagreement between what other stars do and what our tree rings tell us the Sun has done. We observe Sun-like stars producing superflares, events that are 1,000 times more powerful than the Carrington event, on a frequency that doesn't match what we would predict from solar activity cycles. There are 3 possible explanations. 1. Other stars are anomalously active, and the Sun is unusually quiet. 2. Our tree ring frequency estimates are wrong. The events are much rarer than we think. 3. The sun undergoes regime changes that we don't understand, periods of quiet followed by periods of enhanced activity. None of these explanations is particularly comforting, and we're currently in a danger window. Solar Cycle 25 exceeded predictions. The Space Weather Prediction Center forecasted a maximum sunspot number of around 115. The actual maximum was 161. That means we had 30% more activity than expected. That means our models are still incomplete. We are currently in the mid-phase of that cycle, from mid-2025 through mid-2026, and that's when the biggest events tend to happen. The sun is capable of surprising us. It's in the middle of proving it. If you watched our video on how hostile the moon really is, or the Artemis II worst-case scenario, you'll remember we talked about the August 1972 solar particle event. That's a real event. A real solar storm that happened between Apollo 16 and Apollo 17. The radiation dose that an unshielded astronaut would have received in that storm was 2600 rem. That's a fatal dose. The lucky timing was that no one was in transit during that event. Apollo 17 launched just days later and made it to the moon safely. But if the timing had been slightly different, we would have discovered the true lethality of solar radiation in the worst possible way. Now here's the connection. That August 1972 event was a fraction of a Miyake event. It was significant enough to potentially kill an unshielded astronaut. A Miyake event would be 100 times more powerful, and the Artemis missions, the ones that are preparing to put the first woman and the first person of colour on the moon, those missions are launching during a solar maximum. They're flying through the phase of the solar cycle, when the biggest events are most likely, and they're flying past a star capable of violence we have never witnessed in recorded history. We're doing it anyway. Not because we've solved the problem, not because we have perfect protection, not because we've figured out how to guarantee safety. We're doing it because we don't really have a choice. Waiting for perfect safety from the sun means waiting forever. And forever is not an option if you want to go to the moon. The sun rises over the horizon every morning looking exactly the way it did yesterday. The same pale disk, the same warmth on your face, the same star that has sustained life on this planet for 4 billion years, that drives our weather, our seasons, the photosynthesis that produces the oxygen you're breathing right now. It looks stable, it looks reliable, it looks like the most dependable thing in the sky, and somewhere in its magnetic field, in the complex topology of loops and reconnection sites that we cannot fully predict, there is potential energy for something we have never witnessed. Something the tree rings tell us has happened before. Something the ice cores confirm. Something the Kepler data says happens to stars just like ours, on timescales measured in centuries, not millennia. The evidence is there, preserved in wood and ice and the light curves of distant stars. The sun has done this before. It will do it again. The sun is not malevolent. It is not trying to harm us. It doesn't know we're here. It doesn't know we built a civilization out of copper wire and silicon chips and magnetic storage, a civilization that runs on the very electromagnetic forces the sun can overwhelm in an afternoon. It simply does what stars do. It stores energy. It releases energy, sometimes gently, sometimes not. And the only thing standing between us and the next Carrington event, the next Miyake event, the next superflare, is time. Not preparation, not technology, not better forecasting models or more robust power grids, just time. And the tree rings remind us of something humbling about time. Time is the one thing the sun has more of than we do.